Tree decay is an essential process that links tree growth to soil fertility, wildlife habitat, and many other critical functions in the natural forest. However, internal trunk decay can be a major problem for all tree managers. Internal decay presents a problem for both forest product quality and public safety. Knowledge and tools to measure the presence of internal decay are needed by all tree managers, including those in production forestry, those responsible for safe public recreational use of state and national forests, arborists and urban foresters, and those managing trees along utility and transportation corridors. In production forestry, internal decay substantially affects the quality of raw wood materials and ultimately its value in terms of products recovered from the log. Public safety is a major concern when trees and people interact in community settings, in recreational areas, and along transportation corridors. Trees can reach great height, mass, and age. Structural failure can damage property, endanger lives, and affect the efficiency of transportation and energy distribution. Tree decay, poor tree structure, and site disturbance all contribute to structural failure of trees. This fatal accident occurred when undetected internal decay caused a tree to fail into a roadway in the city of Monona, Wisconsin. I'm Dr. R. Bruce Allison, consulting arborist and adjunct professor of forest and wildlife ecology at the University of Wisconsin-Madison. I created this educational presentation to familiarize tree managers with the procedure to detect internal decay in standing trees using a combination of visual inspection plus acoustic and micro-drill tools. Dr. Shaping Wang of the University of Minnesota Duluth and the United States Forest Service are cooperators in the project. First, I will review how decay fungi interact with the tree, and then how and why visible external characteristics of the tree can reveal internal decay conditions. I will explore how traditional methods of internal decay detection using increment borers and sounding mallets have evolved into sophisticated electronic tools of micro-drill resistance and acoustic measurements. Two case studies, one in an urban park and the other in a forest campground, will be presented demonstrating how using these tools in combination allow the tree manager to maximize understanding of a tree's concealed internal condition. Understanding how wood decay fungi interact with trees is the first step in acquiring knowledge on how to detect internal decay. Decay fungi enter standing trees through wounds or breaks in the bark. Wounds can result from a variety of incidents, including storms, logging operations, pruning, or root cutting. Once the decay fungus breaches the bark, it enters the sapwood and can eventually affect the heartwood. There are thousands of different fungal species affecting woody plants, and they can progress over time in succession, one species preparing the way for the invasion of another. Drawings from the United States Forest Service Bulletin, A First Look at Tree Decay, illustrate how decay fungi interact with trees. The living tree structure and its reaction to the presence of the fungal parasite influences how the fungus advances within the tree. Trees wall off or compartmentalize wounded areas to resist the spread of decay, confining it to the wood present at the time of wounding. The concept of compartmentalization was developed by Dr. Alex Shigo as part of his research for the United States Forest Service on the biology of tree decay. Compartmentalization produces chemical and anatomical boundaries that vary in effectiveness to resist the spread of decay. The ceiling and floor and the interior wall are usually less effective than the exterior wall formed by new growth of xylem tissue. Thus, decay tends to move in columns and back to the interior. Understanding how decay advances within a tree allows the tree manager to visualize the shape of internal decay, estimate its point of origin, and predict the direction of movement. The tree manager can use visual inspection of a tree for observing external indicators of internal decay and defect. Seams on the bark, for example, can indicate internal cracks and decay. Other external indicators of decay include open cavities. Fungal fruiting bodies are a sign of the presence of wood decay fungi. They present the opportunity to identify the species of fungus and thereby know its significance and probable course of advancement. Examples of useful wood decay identification books include Wood Decay Fungi and Manual of Wood Decays. The visual inspection of a tree's body language is another way to estimate the presence of internal decay. For example, a tree with an unusually expanded base, sometimes called bottle bud, could indicate the presence of extensive lower trunk decay. Trees are self-optimizing organisms, highly reactive to the environmental stress around them. They are under constant mechanical stresses from holding their own weight, from leans or horizontal branching, or dynamic loads from wind or ice. From Newtonian physics' laws of motion, it is understood that a horizontal force against the tree will produce an equal and opposite resultant force tending to uproot the tree unless there is a reciprocal force to maintain stability. Wind loads in the crown are distributed down the trunk to the anchoring root system as mechanical stresses. The reciprocal force is the weight and friction of the soil against the root system, resisting the shear force. Without it, tree trunks would be like the masts of sailing ships pushed along by wind forces. Internal decay in branches or trunks reduces the area available to pass on those mechanical stresses to the root system. Living parts of trees can respond to areas of concentrated mechanical stresses by laying down additional wood. This process is called thigmomorphogenesis. It explains the bottle shape or bulges that are sometimes evident on trunks with internal decay. Evidence of the self-optimizing growth reaction to environmental mechanical stress is observed in cross-sections of horizontal branches or leaning trunks that have produced wider annual rings on one side, compensating for the extra gravitational loading. Examples of book references discussing this body language of trees and the visible anatomical indicators of decay are The Body Language of Trees and Evaluating Tree Defects. In addition to these visual methods of internal decay detection, tree managers have used other traditional tools including increment borers and sounding mallets. Increment borers allow the visual examination of a coarse sample taken from the trunk using inexpensive, simple tools. But these have the disadvantage of leaving a significant wound at each location sampled. Small diameter drill bits on a battery-powered hand drill can also be used to feel for changes in resistance and look for wound-initiated discoloration in the shavings, but no core sample is produced and results are not graphically recorded. Sounding mallets may allow a trained ear to listen for the telltale drum sounds of internal cavities. They are limited in determining the extent or location and do not produce a record of the sound wave characteristics. Sophisticated electronic tools are available to vastly improve upon these traditional forestry methods. The increment bore and sounding mallet have evolved into sophisticated electronic tools of micro drill resistance and acoustic measurements. The aristography technique was developed in Germany in the late 1980s as a tool measuring the penetration resistance of a thin drill bit. With new electronic improvements, the resistograph tool can now simultaneously measure, display, and record the relative resistance profile as a rotating drill bit is driven into the tree. The resistograph is a portable electric drill with a long metal bit with a narrow diameter only 3 millimeters wide. As the micro drill bit moves through the wood in a linear path, the penetration resistance along that path is measured and recorded. The denser the wood, the greater the resistance. Hollows, cracks, and decayed wood with lower density are detected by the reduced resistance to the drill as it progresses through the wood sample. The pattern of change in density measurements is recorded on scale graph paper or in a digital representation display. Observing the movement of the recording needle, notice how higher readings on the graph indicate the drill bit is encountering greater resistance as it passes through sound wood. A drop in the graph reading indicates the drill is passing through an area of lower resistance formed by decay or a crack or a hollow. The graph now indicates the drill bit has re-entered an area of solid wood in greater density. But here the graph indicates the drill bit is passing through a cavity with no resistance. The cavity continues. Finally, the drill bit completes its passage through the cavity and enters denser wood. The graph scale is 1:1. In this example, it has accurately recorded the change in wood density along the drill path, providing information on the trunk's internal condition. Acoustic measuring devices are used to record the time it takes for an impact-induced stress wave to travel through the wood sample. A stress wave is created with a strike to the tree through an accelerometer that emits a start signal to a timer. A second accelerometer, attached to the opposite side of the tree, senses the leading edge of the stress wave, sending a stop signal to the timer. Time of flight, measured in microseconds, is combined with the measurement of distance between sensors to calculate a transmission time per unit length, such as microseconds per meter, or velocity, such as meters per second. Stress wave propagation in wood is related to the physical properties of the wood. Stress waves travel faster in defect-free wood. Areas of cracks, cavities, or decay-induced low density will require longer times for the stress wave to arrive at the opposite timing sensor. With multiple measurements from an array of timing sensors, computer software can create a projection or two-dimensional map of the acoustic characteristics of the sampled area. Acoustic tomography employs multiple sensors, usually 8 to 32, to measure stress wave transmission times at multiple directions. The distance between the sensors is measured with a caliper scale. An impact-induced stress wave is generated by striking each of the sensor recording points with the hammer. A computer records the stress wave's time of flight to each of the other recording points. Knowing the distance and the time of flight, velocity can be calculated by the computer. Computer projection software using stress wave data from multi-path measurements creates an image of the distribution of relative sound wave velocity in the cross-section. The tomogram in this example is displayed in 4 colors representing varying recorded velocities. Velocities are displayed from low to high as blue, violet, green, and brown. This map of the acoustic characteristics of the sample cross-section with accurate interpretation can determine the size and location of internal trunk decay and defect. Proper interpretation is critical. The tomogram is not a spatially precise map of the internal structure. It is only a representation of the wood's acoustic characteristics as determined by the perceived velocities of stress waves moving between the sensors. Comparisons between the tomogram and the actual tested cross-section illustrate how the tomogram shapes will vary depending upon the type of decay and defect within the trees. Acoustic displays of cracks, for example, are usually overstated in the tomogram. Areas of low velocity could be a result of decay, hollow, snake crack, or ring crack. An effective tree decay detection procedure uses these acoustic and micro-drill tools in combination with visual inspection. The steps of the procedure are: number 1, conduct a simple screening test using a combination of visual inspection and single-path stress wave testing. Number 2, use multi-sensor acoustic tomography to identify the location and approximate magnitude of defects. Number 3, follow up with micro-drill resistance tests to confirm defects or differentiate between decayed wood and internal cracks. The following 2 case studies demonstrate this combination procedure. The first case study was conducted on the Capitol Park trees in Madison, Wisconsin. There were 153 trees in the lawn park surrounding the state capitol building on the heavily used square in the center of the city. The park managers were concerned about tree stability after some tree failures. Here's a video of one of those failures captured on a surveillance camera. The Norway maple damaged a parked car and narrowly missed a group of visiting school children who had just emerged from a school bus. I designed a non-destructive evaluation procedure for detecting internal decay and cracks in the park trees. I started with the visual inspection of all directly and indirectly observable defects. This, of course, required climbing into many larger trees. There were 12 squirrels living in this large cavity in heartwood decay. Next, I employed the single-path stress wave tool to perform quick and inexpensive screening tests of the lower trunks of all larger trees. I conducted 2 tests at right angles to each other at varying heights on the trunks. The results were compared to the anticipated stress wave velocities in comparable tree species. Those tables are published in the United States Forest Service report, Assessment of Decay in Standing Timber Using Stress Wave Timing Non-Destructive Evaluation Tools. These tables offer a range of values only. There are no uniform reference standards. Stress wave velocities of solid wood can vary due to moisture levels and tree growing conditions. Therefore, it is important to conduct a self-reference test on a part of the tree or a comparable neighboring tree that is known to be sound. In this study, if the sampled cross-trunk section had a velocity reduction greater than 25% of the solid wood reference standard, it failed the screening test. Multi-path acoustic tests were then conducted on trees with possible problems, as indicated by the visual and single-path stress wave test. The multi-path acoustic test generated tomograms requiring interpretation to identify the type, size, and location of internal trunk defects. In the case of this 100-year-old red oak, tests at cross-section elevations of 10 centimeters, 100 centimeters, and 200 centimeters indicated decay and defect most severe at the root collar level. Tomography software is able to combine the 3 tomograms creating a 3D representation of the study area on the trunk. Resistograph tests were required to verify the exact type and extent of the suspected defects and decay indicated on tomograms. The value of tomograms in those cases was that they identified the best location for drilling, significantly reducing the number of drills required and enhancing the value of the data acquired. Resistograph testing indicated snake cracking in a large area of heartwood decay at the root collar area of the red oak. Having carefully progressed using the procedure in gathering and interpreting the data, I had confidence to recommend the removal of this historic and very public tree. Measurements of the defect, knowledge of the way decay interacts with the wood, and understanding the physical requirements for mechanical tree stability led to the conclusion that this tree had a high probability of failure under loading due to trunk cracks and root collar decay. This lower trunk section fell apart as it was removed due to the decay and advanced cracking. A 300-page report was submitted to the park managers detailing the cases of internal decay and defect revealed using these combined non-destructive testing methods. Select tree removal and pruning were conducted based on the report's conclusions. Just weeks before the last 2 trees were to be removed, a violent storm with unusually high-velocity winds passed through the Capitol Park, causing these 2 remaining trees to fail. Of the remaining 143 trees in the park, the only trees to fail were those 2 that had been identified as at risk using the procedure. Seldom does nature cooperate so fully in validating a procedure for testing tree stability. Another example of the successful use of combined visual, acoustic, and micro-drill decay detection procedure occurred at a recreational ropes course located at the United States Forest Service's Camp Nesbitt in Upper Michigan. The recreational course consists of steel cable and ropes attached to a cluster of 12 60-foot tall red pines. Groups of school children regularly use the course, mounting the high suspended walkways and swinging from ropes. Undetected internal decay within any of the trees has the potential for disastrous consequences. A team of scientists from the United States Forest Service Forest Products Laboratory, Michigan Technological University, and the University of Minnesota Duluth were asked to non-destructively evaluate the trees for evidence of internal decay and instability. First, a visual inspection was conducted, looking for cavities, cracks, seams, bulges, fungal fruiting bodies, carpenter ants, or other evidence of decay. Then single-path stress wave tests were conducted on the lower trunks and at select locations in the upper crown. To establish a standard for stress wave velocities of solid wood in this particular stand, we conducted stress wave tests on red pines known to be without decay or defect. At those locations where visual inspection and single-path stress wave tests indicated problems, multi-path acoustic tests were conducted. Tomograms from those test sites were interpreted to determine an estimate of the type, size, and location of internal decay and defects. Using the acoustic map of the sampled cross-section to guide the entry point and direction of the micro-drill, additional crucial data was gathered while minimizing the number of drill holes. The combined use of time-saving visual and single-path stress wave screening tests also reduced the use of the multi-sensor tomograph test. By using the tomograph to guide the number and direction of micro-drill tests, fewer drill holes were needed and more meaningful information was gathered. Single-path stress wave testing in 2 directions takes less than 5 minutes. Each micro-drill test also takes about 5 minutes. Multi-sensor tomographs with setup and measurements require around 30 minutes per cross-section tested. Only one of the 12 tested trees was determined to have significant internal decay and removed from the course. It is important to keep in mind that the mere presence of decay, even extensive decay, is just part of the story in determining whether a tree should be removed. These case studies illustrate that a combination of non-destructive tests after visual inspection is effective at detecting internal decay. Screening with a quick, single-path stress wave test is followed by a more complex, multi-path acoustic testing as needed with the use of a few directed microdrill tests to assist in interpretation. This procedure offers managers an efficient method to measure hidden internal decay and defects in standing trees. Only the expense of the tools keeps this procedure from becoming an industry standard. Following are listings of relevant equipment manufacturers.